Dear students, in this lecture, we are going to study about what is the relationship between line and phase quantities in three-phase system. So, first of all, what is three-phase system? Any system utilizing more than one winding or one phase is called polyphase system. Polyphase system is nothing but three-phase system. So, any system utilizing more than one phase or one winding. Phase is nothing but one phase is nothing but one winding. So, any system utilizing more than one winding is called polyphase system. It is also nothing but polyphase system is also nothing but three-phase winding or three-phase system. A three-phase system has three sinusoidal voltages of equal amplitude and frequency. So that a three-phase system has three sinusoidal voltages of equal amplitude and frequency, but they differ in phase by 120 degrees from each other. So three phases are displaced from each other by 120 degrees. If you want to calculate phase angle between the any adjacent phases equals to, for three-phase system 360 by 3, for four-phase system 360 by 4. So each phase displacement between each phase equals to 90 degrees. For three-phase system, the phase displacement equals to 120 degrees. Similarly, for n-phase system, 360 by n. Here where n is the number of phases. Like that, we can calculate the phase displacement between the adjacent phases. So that for three-phase system, three phases are equally displaced by from 120 degrees. So that in three-phase system, three independent windings or phases are displaced by 120 degrees. So the phase voltages are represented by VR of t, Vy of t, Vb of t. So three phases are represented by RYB. In India, standard notation is three phase. Three phases are represented by RYB. That means VR, Vy, Vb. So three phase voltages are represented by VRN. First phase voltage VRN. VR phase voltage equals to Vm sin theta or Vm sin omega t. In theta or omega t both are same. So Vyn equals to Vm sin theta minus 120 degrees. That means Vm sin of omega t minus 120 degrees. Similarly, third phase Vbn equals to Vm sin of theta minus 240 degrees, or else Vm sin of omega t minus 240 degrees. For a balanced system, for a balanced three-phase balanced system, the RMS value of phase voltages, as we know that RMS value equals to maximum voltage by root 2. So similarly, the RMS value of phase voltage equals to VRN, VYN, VBN. For balanced system, each phase voltages are same. VRN equals to VYN equals to VBN equals to maximum voltage by root 2. In this way, we will calculate the RMS value of voltage. So for three-phase system, three voltages are displaced by 120 degrees. VRN, VYN, VBN. So the phase angle between the any two phases, the phase angle between the any two phases equals to 120 degrees. Similarly, here also 120 degrees. Similarly, here also 120 degrees. So the phase angle between any two phases. Similarly, we can also represent the three phase voltages in polar form. So as we know that already, Vm sin omega t also written as Vm at an angle 0 degrees, reference phase. That means this phase is starting from 0 degrees. So Vm at an angle 0 degrees, Vrn at an angle 0 degrees. Similarly, Vm sin of omega t minus 120 degrees can be written as Vyn at an angle minus 120 degrees. Similarly, B phase Vbn can be written as at an angle Vbn at an angle minus 240 degrees. So in this way, three phase voltages are represented. Here we can see the three phase voltages. This is the R phase voltage. So R phase voltage is always Vm at an angle 0 degrees. Always this is the starting at 0 degrees. Next Y phase. Y phase is starting from 120 degrees. After 120 degrees Y phase will come. Similarly, after one more 120 degrees B phase will come. So in this way, three phase voltages are generated. This is R phase voltage, red color. R means red color, Y means yellow color, B means blue color. So in this way, three phase voltages are generated. What are the connections of three-phase system? What are the connections of three-phase system? We have two types of three-phase system. We have two types of three-phase connections. One is the star connected system and another one is the delta connected system. So in this way, again star connected system will be subdivided into three groups. Type of connection, star connection, and terminals are available. Number of how many conductors are required, used. So for star connected system, again further divided into two types: three-phase three-wire system, three-phase four-wire system. Basically, three-phase three-wire system will be used at generating side. Three-phase three-wire system is used at generating side. Similarly, three-phase four-wire system is used at distribution side. We are under the distribution side. So and delta connection, neutral fourth wire will not be available. Neutral point is will not available. So that delta connection, three-phase three-wire system only. This is used at for high power transmission lines. For high power transmission lines, delta connected systems are used. For three-phase three-wire system, three conductors are required. For three-phase four-wire, four conductors are required. Similarly, three-phase three-wire system, delta connected system, three conductors are required. So in this lecture, we are going to see the relationship between phase and line quantities in star connected system as well as delta connected system. First, we will see the relationship between phase and line quantities in star connected system. In star connected system, all the finishing points are starting points are joined together. So in star connected system, all the finishing or starting points are joined together, and other ends of the three windings or three coils are connected to the load. So this connection is nothing but star connected system. All the either starting or finishing points are joined together and other ends are connected to load. So the common point where all the finishing points or all the starting points are joined together is also called as neutral point or star point. Neutral point or star point. For balanced three-phase system, three-phase impedances are equal. Z1 equals to Z2 equals to Z3, as well as three-phase voltages also same. VRN equals to VYN equals to VBN. For three-phase balanced system, three-phase voltages are equal and neutral current is zero. For balanced system, there is no current flowing through the neutral wire. Neutral wire is nothing but fourth wire. So three-phase three-wire four-wire system basically used at a distribution system. So as we know that star connection is nothing but all the either star finishing or starting points are joined together. So here all the finishing points are joined together and the remaining ends are connected to load. Here load will be connected. In this way, I will connect the star connected system. So this is R phase, red color, yellow color indicates yellow color phase or coil indicates Y phase, blue color coil indicates B phase. So this three phase windings are all finishing points are joined together. This point will be formed as a neutral point. This point will be formed as a neutral point or common point or star point, where all the starting or finishing points are joined together is known as neutral point. For balanced system, neutral current equals to 0. So here we can observe the line voltages as well as phase voltages and phase currents as well as line currents. Here R phase, I1 represents the current flowing through the R phase. Similarly, I2 represents the current flowing through the Y phase. Similarly, I3 represents the current flowing through the B phase. So I1, I2, I3 represents the I1, I2, I3 represents the phase currents of respective phases. Similarly, VRN represents the phase voltage of R phase. Similarly, VYN represents the phase voltage of Y phase. Similarly, VBN represents the phase voltage of B phase. So I1, I2, I3 are phase voltages, phase currents. Similarly, VRN, VYN, VBN are the phase voltages. For balanced system, all three phase voltages are equal. VRN equals to VYN equals to VBN equals to V phase only. Similarly, here R phase, this is R phase, this is Y phase, this is B phase. Here load will be connected. So that the IR is nothing but current flowing through the R phase, IY is nothing but current flowing through the Y phase, and IB is the current flowing through the B phase. Similarly, VRY, the voltage between the any two lines, the voltage between any two lines is nothing but line voltage. That means if the voltage between R phase and Y phase is represented by VRY, similarly the voltage between Y phase and B phase is represented by VYB. Similarly, the voltage between B phase and R phase is represented by VBR. So here I have represented all the phase voltages and phase currents. Similarly, line voltages and line currents. VRY line voltage, VYB line voltage, VBR line voltage. Similarly, IR, IY, IB are the line currents. IR, IY, IB are the respected line currents. So that here we can see the what is the relationship between phase current and line current. What is the relationship between phase current and line current? Here already as we have derived, I1 is nothing but I2 is nothing but I3. I1, I2, I3 are nothing but phase currents. Already we have defined. Similarly, IR, IY, IB are the line currents. Then we will see the what is the relationship between phase current and line current. Here I will apply the KCL at point U. Apply the KCL at point U. KCL is nothing but the sum of incoming currents equals to sum of outgoing currents, or else algebraic sum of currents meeting at junction or node equals to 0. Here at point U, at this node, the incoming current equals to I1 and outgoing current equals to IR. Similarly, I will apply the KCL at point V. So sum of incoming current I2 equals to sum of outgoing current IY. Similarly, I will apply the KCL at W, point W, sum of incoming current I3 equals to sum of outgoing current IB. So that I1 equals to IR, I2 equals to IY, I3 equals to IB. So in this way, we will define the what is the relationship between phase current and line current. So that finally phase current I1 equals to line current. So for three phase star connected system, phase current equals to line current, or line current equals to phase current. So this is the conclusion for star connected system. What is the relationship between line current and phase current? Both are same. Phase current equals to line current. Now we will see the what is the relationship between phase voltage and line voltage. What is the relationship between phase voltage and line voltage? Similarly, for finding the voltages, I will apply the KVL in this mesh. So here already I have defined phase voltages and line voltages. Phase voltages are VRN, VYN and VRY. So here I have taken in this mesh. I will apply the KVL for finding the what is the relationship between phase voltage and line voltage. So here I have taken this part. The voltage between the R phase and Y phase. I am deriving. What is the relationship between this is the line voltage, this is the phase voltages. So here I will apply the KVL in the mesh U, R, Y, V, N and U. So in this mesh I will apply the KVL. So minus VRY equals to minus VYN equals to plus VRN equals to 0. The algebraic sum of all branch voltage in a closed mesh equals to 0. So VRY equals to VRN minus VYN. So the line voltage equals to line voltage is nothing but between the two lines VRY, between the R phase and Y phase. VRY equals to vector difference between the two phase voltages. Here I will written the VRN. This can be also written as plus minus VYN. This can be also written as VRN plus minus VYN. So this is the vector sum of VRY plus minus VYN. So vector sum of VRY equals to vector sum of VRY, vector addition VRY equals to VRN plus of minus VYN. Similarly, Vyn Vyb equals to, similarly, if you apply the KVL between this in this mesh, similarly apply the KVL between in this mesh Vyb, similarly VBR, we will get the line voltages. Vyb equals to Vyn minus Vbn, Vbr equals to Vbn minus Vrn. Here I will show the parallelogram method for vector addition. Parallelogram method for vector addition. Already we have studied in intermediate level. What is the parallelogram method law for vector addition? This is the vector A, this is the vector B. I want to add these two vectors. I want to use add these two vectors by using parallelogram method. This is the, if you want to add this vector with this vector, draw the parallel line. Similarly, if you add to this vector with this vector, draw this parallel line, and both will intersect here. This is the resultant C vector. So C vector equals to vector addition of A plus B. So for getting the C equals to square root of A square plus B square plus 2AB into cos phi. How we will get this formula? If you extend this graph, here 90 degrees will make. Here 90 degrees will make. What is the phase angle between here? This is the same phase angle. Here also same phase angle phi. So here O, I will indicate the O at this point. From this right angle triangle, O, C, here D. Suppose from the right angle triangle OCD equals to hypotenuse square equals to side square plus side square. OC square equals to OB square plus BD square. OB plus BD whole square. OB plus BD whole square plus CD square. CD square. So here OB is nothing but B. Similarly, BC is nothing but A. Similarly, BC is nothing but A. Here BD equals to A cos phi or cos theta. Similarly, CD equals to, this is a parallel line. CD equals to A sin phi. If you apply the OB plus BD whole square equals to, if you apply the substitute the OB plus BD whole square plus CD square, we will get this equation A square plus B square plus 2AB into cos phi. Here basically this angle, if it is angle equals to 60 degrees, we will apply the cos 60. So A square plus the magnitude of two vectors will be remain same. The vector magnitude of OA, OB will be same. So square root of A square plus 2A into cos 60. Cos 60 equals to 1 by 2. 2 will get cancelled. So finally root 3 into A square, C equals to root 3 into A. So this method is, I will apply for what is the relationship between phase and line voltages. Parallelogram law for vector addition. As we know that in three-phase star connected system, three-phase voltages are displaced by 120 degrees. VRN, VYN, VBN. So I want to draw the VRY. VRY is the VRN, phasor sum of VRN minus VYN. VRN is here. Here this is the VYN, positive. If you project this oppositely exactly 180 degrees phase shift, this is the VYN. So here, so the vector sum of VRN plus of minus Vyn, we will give the Vry. It will give the Vry. This is the Vry. So similarly, we will draw the Vyb. Vyb equals to Vyn minus Vbn. So Vyn is here, minus Vbn equals to here. If you project this is the exactly opposite, minus Vbn will be obtained. Similarly, Vbr equals to Vbn minus Vrn. So minus Vrn will be in this side. So this is the VBR. VBR. So in this way, we will draw the phase voltages as well as line voltages for three-phase star connected system. So I will take this point. If you take any point, both the same formula will be obtained. Same value will be obtained. I will take this part. How what is the value of VYB? VYB equals to same parallelogram method is used for the vector addition. V by n plus square a square plus b square plus 2ab into cos theta. Similarly, V by n square plus VBN square plus 2 V by n VBN of cos 60. So here from year to year 120 degrees. Here this line voltage will make the exactly half make. So here 30 degrees will make, here 30 degrees will make. Total 60 degrees from year to year 60 degrees, remaining from year to year 60 degrees. Total 120 degrees. So cos theta equals to 60 degrees. So V phase square. For balanced system, all three phase voltages are equal. So VRN is nothing but VYN is nothing but VBN is nothing but V phase. V phase square plus V phase square plus 2 V phase into V phase. Cos 60 equals to 1 by 2. 2 will get cancelled. So root 3 into V phase. So therefore similarly VRY equals to root 3 into V phase. Similarly VBR equals to root 3 into V phase. So in this way we will obtain the relationship between line voltage and phase voltage. This is the line voltage. This is the phase voltage. So for three-phase system, three-phase star connected system, line voltage equals to root 3 times of phase voltage. This is the conclusion for star connected system. So line voltage equals to root 3 times of phase voltages. For line current equals to phase current only for star connected system. Whereas relationship between line voltage and phase voltages, line voltage equals to root 3 times of phase voltage. This is a conclusion for what is the relationship between phase and line quantities in star connected system. Next lecture we will see the delta connected system. Thank you.